Hello. Okay, so we will look up. We will come back to Fourier series, and I will try to address the doubt which some of you had pointed out during the last Wednesday class. As far as it was regarding convergence, and as far as I remember, it was you were asking how when we add the error terms, we still the error terms are non-zero, and the by adding several non-zero terms we are still getting a zero as the energy of the error. Okay, so I think that was the question asked, but I will attempt to explain the convergence again of Fourier series, and hopefully this might help to clear up some of the doubts, because there are something more involved here, and we are not gone into those kind of details. And again, here also we are not getting into details. To get into the real mathematics behind it, you should look at a book on Fourier analysis, but our treatment will be just enough to understand why the convergence is explained in the way I am about to do it. So, okay. So let me begin by. Okay, fine. Okay, good. So first, let us say what are we saying in the Fourier series? What are we saying in the Fourier series? This is what we are saying. There is a periodic signal with period t naught. X of t is that periodic signal, and we are representing x of t as a linear combination of complex exponential signals. Okay, and the coefficients of the linear combinations are ak's, and you can obtain the ak by the Fourier analysis formula. Okay. Now, first thing is we have to make sure that the ak exists. So a sufficient condition for ak to exist is that x of t be absolutely integrable over a period. So if this condition is there on x of t, that is the absolute integral of x of t is less than infinity, then we are sure that ak is a bounded number. So ak will exist. Okay. So this is the one condition for the Fourier series coefficients to exist. Now, another question we can ask is, how valid is the Fourier series representation? That means this summation here, it is an infinite sum. Okay, so infinite sums may converge, may not converge. So how can we be sure, or what can we say about the convergence of this particular infinite sum? Okay, or how good is this representation? How can we say that this representation is actually coming up to x of t? Okay, so we can do that by, let us do that by analyzing the partial sum. So this is the same expression in the textbook, 3.47. So in this partial sum, we have k equal to minus n to n. We have 2n plus 1 terms, and this is the partial approximation xn of t. Okay, and we also represent the error at capital N is En of t is equal to the original x of t which we are trying to approximate, and the approximation with this partial sum. Now, how to measure the goodness of the representation? We need a metric to measure how good is the partial sum. How good is this? So for that we will use the energy of the error. So this is the metric we have decided to use. Okay, so energy of the error, this same error over one period, is what we will use, and that we will call it as En. So now we should look slightly, we should look back and look at some of the ways in which infinite series converge. So before that, let's see, if x of t is a piecewise smooth function, that means it has a finite number of discontinuities. Okay, it is piecewise smooth. Okay, and we also consider the Dirichlet conditions, which kind of ensure that the Fourier series exists for most practical signals, by ensuring that the pathological signals, which contains too many discontinuities or multiple number of maximum minima, those kind of functions are excluded. So by using the Dirichlet conditions, we can be sure that most practical, I mean, like we look we look into only more practical signals. So that will, these conditions will help us. Okay, so one way as an infinite series can converge is by what is known as uniform convergence. So in uniform convergence, let's come back to this partial sum here. Suppose this is the partial sum, and let us assume that n becomes greater and greater. Okay, n is slowly becoming to infinity. But even if n is not taking the limiting value, but still, even for any partial value, some series will converge in a uniform manner. What that means is that for every value of t, or at every value of t, this representation, this partial sum, will approximate your x of t, this partial sum, or this, okay, let me write this xn of t approximates x of t at every value of t with less than or equal to some error. Okay, this error could be like 0.001 or something, but as long as if the sequence converges uniformly, this condition that the error is less than some constant is met at every t. Okay, another way of convergence is pointwise convergence. So pointwise convergence is little more difficult. I mean, uniform convergence is ideal convergence. This if all series have this, then we are very happy. But some series may not have this, so we also go in for pointwise convergence, in which the definition is slightly different. It is again the partial sum here. We will still use the partial sum, this partial sum, but the thing is that to get a particular error, to make sure that the representation is less than a particular error, we might have to use different n's for different t's. Okay, so if it is not uniform but it is pointwise convergence, you might need to use at some t's you might need to use a larger n, whereas at some t's you might need to use a smaller n to get this error which is less than some given epsilon. So that is pointwise convergence. Now suppose we represent x of t with xn of t as n tends to infinity. Okay, so now the interesting thing is that if you write it in the Fourier series form, at all points where x of t is continuous, xn of t equal to x of t as n tends to infinity. Okay, so wherever x of t is continuous, your partial sum will be equal to x of t at n tends to infinity, and this convergence will be uniform. Now if there is a discontinuity, your partial sum is going to become the average value of the the right limit and the left limit. Okay, so what this basically means is that at the discontinuities, xn of t will never converge to x of t. Why you may ask? See, whenever there is a discontinuity in the function, we are using smooth functions, which are basically sinusoids, to represent a function which is discontinuous. Okay, so no matter how many sinusoids or how many number of harmonic sinusoids you use, even if they have high frequency and they oscillate fast, you will never be able to approximate, or you will never be able to equate a discontinuous function with a smooth function. Okay, so this, at the point of discontinuity, the approximation will always be, the partial sum will always be an approximation, even if n tends to infinity. But if x of t is continuous everywhere, xn of t converges uniformly to x of t. Okay, so if there is continuous, the function is completely continuous, then there is no problem. At every point you will have uniform convergence. So when the x of t is discontinuous, convergence is not uniform. Okay, it is not even uniform, it is not even pointwise. So the basic idea is that the smoother is x of t, the easier it is to represent with a finite number of partial sums. So for such cases, because see, discontinuous functions, the simple square wave which we saw, it's a very simple function and it is a very useful function. Later we will see that it is a very useful function. So we cannot say that we cannot represent such functions using Fourier series. So since we want to represent, we want to get the Fourier series representation for such signals, we define yet another type of convergence, and this convergence is called convergence in the mean. Okay, so this convergence in the mean means that precisely x of t minus xn of t the whole square, the energy of the error tends to 0 as n tends to infinity. So we are saying that we will call this non-converging series as converging in the mean if this condition is satisfied. Okay, so as long as the energy of the error tends to 0 as n tends to infinity, then we will say that the partial series representation, partial sum representation will converge, and I am willing to accept that convergence. But the catch is that this convergence in the mean does not require that E of t equal to 0 at all t. Okay, so that means, like for example, this is, I have shown E of t here. So this is the period t naught. So in this, within this period, there is a non-zero value here at t naught, okay, small t naught. Okay, so at this point, there is a non-zero value. But still, if you find out the energy of the error in this period 0 to t naught, you will still get it as 0. So what this means is, even if you have convergence in the mean, the energy of the error need not be 0 at all points. It is possible that the energy of the error could have non-zero values at isolated points, and still it will still converge in the mean. So this is precisely what is happening when you represent discontinuous functions using Fourier series. The convergence is defined as convergence in the mean, and the error could have non-zero isolated points. It could be non-zero at isolated points. So it need not, when a series converges in the mean, it need not converge to x of t at all t. So this is the explanation for the Gibbs phenomenon. And now what is the criterion? What is the criterion to ensure that a periodic signal x of t has a Fourier series that converges in the mean? So to this condition, if the energy of the x of t over one period is bounded, is a finite value, then that is a sufficient condition for convergence in the mean. Okay, so if you remember the earlier case, we said it should be x of t must be absolutely integrable for the AKs to exist. So now if x of t has discontinuities, we to ensure convergence, we will relax that and say that as long as x of t, the energy of x of t within a period is bounded, then it will converge in the mean. X of t, the partial sums will converge in the mean, and that is why we are able to have Fourier series for these discontinuous functions.